Okay, so for this question, it is asking about action potentials and graded potentials. And so, given the fact that graded potentials precede action potentials, I want to start by talking about graded potentials. So, what I will do first is draw a graph, which would be the best way to describe these potentials. So, on the x-axis, we have time, and here we have the resting membrane potential. So we know that the resting membrane potential of a neuron is here around negative 70, and we will put 0 up here. And so on these graphs, we have here this line, which will represent our threshold. And the threshold is the point at where this resting membrane potential reaches the threshold that will cause an action potential. So to start off with graded potentials are determined by the opening of ligand-gated channels. And so there are two different things that happen with these graded potentials on this graph. I'll do a little representation here. So if we are here at negative 70 and a ligand-gated channel for sodium is opened, and there is sodium that enters into the cell, then this potential will increase or go more towards 0. It will move up like this. And so this movement of increasing is called depolarization. Because we're originally in a polarized state, if the resting membrane potential increases, we are then depolarizing. And so I will erase this. And so what happens with a depolarization is that the membrane potential will go closer to 0. It will increase. But with graded potentials, it will always come back down to where it was, and it won't ever reach this threshold value. So the other thing that graded potentials can do is they can go down like this. And this action of decreasing or going further away from 0 or threshold is what's called hyperpolarization. And so this is what would happen if this resting membrane potential becomes more negative. So this would be an instance where there's sodium, or there's positively charged ions leaving the cell. That would cause the inside of the cell to become more negative. And like I said before, these graded potentials won't ever reach this threshold value. And the thing about graded potentials that makes them graded is that the amount of stimulus, or let's say the number of channels that are opened or closed, can contribute to the amplitude or the size of the stimulus. So if there's only a couple channels open or closed, then we might have a depolarization that's really small like that. But if we have a lot of channels that are open, then our depolarization can be really, really high like that. So that's what causes these potentials to be graded, is that they can be summed with the other channels opening and closing and the other stimulus that is happening. Okay, so now we've talked about graded potentials. We're going to talk now about what happens after these graded potentials, which is action potentials. So action potentials occur when this resting membrane potential will depolarize up to the point where it hits this threshold. And once it hits this threshold, it will undergo a little shape like this, which is kind of the generalized shape of action potential with the changing of the membrane potential. So the phases of the action potential, here we will call the rising phase. Here we will call the falling phase. And here, which which we talked about before, is hyperpolarization. So the rising phase is our depolarization, and the falling phase is our repolarization. And so to talk a little bit about this action potential, we'll go ahead and split it up into sections. So the section here of the peak of the action potential is what's called an absolute refractory period. And in this period, in this time of the peak of the action potential, there cannot be a second action potential that takes place during this time. And so this second period here, this part is called the relative refractory period. And in this section, there can be another action potential that is started, but it will take more of a stimulus because we see the value coming down here in this hyperpolarization. It's going to take a lot more for that action potential to begin, for it to reach the threshold. And so to kind of break up the different parts of the action potential, I'll go ahead and label this graph here, and we can talk about what happens at each one of these positions. So we'll have point 1, have point 2 here, point 3 here, 4, and 5. So I'll go ahead and write these out. So what happens at number 1 is a graded potential, which is what it starts as, reaches threshold. And what happens, the threshold is determined by the voltage-gated sodium channels. And at this point, they become open, and sodium is rushing into the cell, which is causing this dramatic increase, this getting closer to zero and even passing zero in a lot of cases. A lot of those positive ions going into the cell. So number 2, we have the voltage-gated potassium channels begin to open, and the voltage-gated sodium channels begin to close. Because that is showing the change here from the increasing, and will reach the top of that peak and then begin to decrease. So in number 3, the voltage-gated sodium channels are closed, and the voltage-gated potassium channels are open, and the potassium rushes out of the cell. Down when we reach point number 4 at the end of this absolute refractory period, the potassium channels are closing, and the rush of potassium slows down. And down here at number 5, at the hyperpolarization, the potassium leak channels opened. And that will cause this hyperpolarization, and then it will go back to this resting membrane potential here. And so those are the different phases of the action potential and the channels and ions involved with each section. All right, so now I'm going to talk a little bit about capacitance, the time constant, and the length constant. So to start with capacitance, capacitance is basically the measure of the separation of charges on a membrane, which can be given by Q divided by the volts. So to kind of explain this equation a little better, I'll draw two membranes here to kind of show the separation of charges. And so if this right here is representative of the positive on the outside and the negative on the inside, this right here is the distance between these charges. And so drawing this one over here, we can see that there is a greater length between these charges. So here we're going to have a higher capacitance, and this one will give us a lower capacitance. So the thing about capacitance that's interesting is that we see here that there are a higher concentration of positive charges here in this membrane, and there are a lower concentration here. So because of this ratio, we know that these two membranes can be at the same potential. Because of this ratio, there are higher concentration of charges on this membrane and a lower here, but this one has a greater length than this one. And so those two variables of the separation of charges per volt or per the amount of charges that there are on a membrane are what determine capacitance. Okay, so now we're going to talk about the time constant, which is equal to the amount of time that it takes to depolarize a certain part of the membrane. So the time constant is equal to the membrane resistance times the capacitance. So with capacitance, what we just talked about is the separation of charges per volt, and the membrane resistance is basically the ability of ions to pass through the membrane. So if we take a neuron here, and let's say that it's myelinated, this myelin is going to increase this membrane resistance because it's harder for ions to travel out of the cell because they cannot pass through these myelin. So as the resistance increases, the time constant will increase because it will take a longer period of time for this depolarization to happen, simply because the myelin on these neurons will cause it to be really hard for ions to pass in and out of the membrane. Specifically for a neuron, though, the resistance of the membrane increases while the capacitance decreases. So this time constant, the effects of the time constant on a neuron will be fairly minimal. So now discussing the length constant, given by lambda is equal to the square root of the membrane resistance over the internal resistance. So because these two factors are inversely related, I'll kind of draw a picture of this. So here we have the positive sphere of influence that is constantly depleting as it moves down the cell. So just like we talked about before, the membrane resistance is increased when we have myelinated neurons, which will allow the sphere of influence to travel further, which is this one right here. But if we have internal resistance, then there will be things inside the neuron that will either dissipate this sphere of influence or cause it to fizzle out a lot sooner. So, because this resistance contributes to the ability of the length of the sphere of influence traveling down the neuron, and the internal resistance is inhibitory for the sphere of influence traveling down the neuron. The length constant is the actual distance that the sphere of influence is able to travel down the neuron. And it is calculated by taking into consideration the membrane resistance, dividing it by the internal resistance, and finding the square root of that. Okay, so the last part of this question asks us to talk a little bit about the synapse. So I'm going to draw a little bit of a picture here. So right here we have the synapse. Here we have the soma or cell body. We have the dendrites. And this right here is the axon and the axon terminals. So we know that a signal will go down this direction from the cell body down the axon to the terminals, and then will send itself to a nearby neuron onto its dendrites. So the dendrites are the receiving end and the axon terminals are the sending end. So what I'm going to do is kind of blow up this little picture right here to kind of give a better explanation. This here is the axon terminal of the first neuron sending to the dendrite of the next neuron. So the way that this happens is that there are different neurotransmitters that get sent down the cell this direction. And so these neurotransmitters will get picked up in these transporters and will then be pushed out of the cell into this area here, in between the two neurons. And on the dendrite of this second neuron, there are receptors that will be specific to the certain type of neurotransmitters that get sent into this area. So there will be neurotransmitters that can bind to these certain receptors, which will then in turn cause another sphere of influence of positively charged ions that will send its way down the next neuron. And so that here, if this is the first part of the synapse, we will call this the presynaptic terminal. And we know that this end will then be the postsynaptic terminal. So we know that these neurotransmitters and these signals go from the presynaptic terminal to the postsynaptic terminal in this fashion.